All right, it is time to begin, so if you'll take a seat here. Looking at the record, thank you. Looking at the record, I don't see Maranatha. Is she feeling bad again? Well, I spent 6.5 hours yesterday grading your exams. Yes, so I have the equivalent of 11 exams done. Everyone in the other class here. Wow. Yeah, so I figure I only have 25 more hours of grading before I have them all done. Yay. So far, though, here's what I was doing, okay? I go through and I just check the answers on the exam, and then I was grading the first 5 because those are shorter than the second 5. And of the 17, I think, that I started, there were 5 that had all of the right answers circled. And so I graded all of those. And I think we have 3 perfect papers already. So, that's encouraging. There are some that aren't as perfect, and those I didn't finish grading. And so, yeah, that's the progress I'm making. I will work on it again Sunday and Monday and Tuesday and Wednesday and next Thursday. And hopefully by then I might have them done. But I told myself I was not going to give you all of the feedback on what you did wrong, but I can't do that. I want students to be able to learn from their exam. So please do look over your exam when you get it back so you can see what you lost points for. And then you can ask me and, challenge me. I don't think that was right what you marked off, right? It's your prerogative. I want you to be comfortable with your grade and to have the right grade. So getting started, today will be, I guess, our final day of exclusively looking at forces. And what I've been doing in the last 2 actual lectures, last Friday and then this past Wednesday, is introducing forces and how we work force problems along the way. So actually, as we go through today's lecture, I'm actually going to do one of the homework problems that's due tonight. Remember, they're due like 7:30 tonight because sundown keeps moving earlier and earlier. Just to give us a little more practice in solving problems. So we ended last class period talking about tension. I had my little demonstration illustrating tension. I didn't get to do everything I wanted because of time, but it's important that we understand tension is a force distributed through something like a cable, a cord, a rope, a chain. You can't have tension in a liquid. You actually don't have tension in a solid. In a solid, you have a tensile stress. And in a liquid, you cannot have any tensile anything. So tension is, when we talk about tension, it's going to be something in a cord. And tension has units of newtons. It's a force, but it's the force transmitted through the cord. And anywhere it touches something, it produces a force equal to the tension. And so, we've done things like this little mass here. I'll warn you right now, we're starting to get to a clicker question right now. So, get your clickers out. While you get your clickers out, I'm going to try to change this to full screen because it sometimes just forgets. Okay, so here is our clicker question, and you cannot answer yet. I have to move the slide forward so you can answer now. Which statement is untrue of tension? Okay, I'll give it another 12 seconds. Okay. We had 4 that said that, 4 that said that, 41 that said that, and 4 that said that. Now this time, I'm going to bring out the cards and ask whoever's name is on this card, which is Benjamin St. John, or if you were a volleyball player, it'd be St. John, because that was St. John Smith's first name, St. John. Okay, so Benjamin, tell us your answer and your reasoning behind it.
Not here.
Oh, not there? Uh-oh. Okay, moving on then. How about Teresa Cody?
I chose C because I think tension will be from them.
Because you think tension is what?
No, I chose safety that not for tension on the acts of the disease. Sorry.
Could you guys make it out? It could be my hearings. No.
I chose C because the tension on the acts on solids and liquids at the test.
Okay.
She said it only works on solids and liquids.
Okay, the fact is tension doesn't work on there is no kind of tension at all in a liquid. And that's why this was correct, because you can't have a tension in a liquid. In a solid, you can have a tensile stress. We typically wouldn't call that tension, but it's a tensile stress. In a cable, that's where we define tension. Question, Colton.
Yeah, I was just going to ask, I chose C, but what about, how different is surface tension or the interaction of molecules?
Okay, I have a student that asked a question about how does this relate to surface tension. Surface tension is taking the idea of tension and applying it to a two-dimensional surface. So you have a two-dimensional surface, and there are forces between the molecules that hold them together, so they're bound together. And then when you place something on it, the force that's holding them together acts like a tension. And so when we get to talking about surface tension, what we learn here on tension, we can apply there to surface tension because it's basically a two-dimensional expansion of the one-dimensional tension idea. Okay, so the answer that was untrue was tension actually solids and liquids, because you absolutely have nothing tensile at all in liquids, and solids can have a tensile stress. But the word tension is usually reserved for something like a cord or a cable, a chain. The other things here were correct, and of course, it's more important than focusing on the incorrect is focusing on the correct. So tension is a force. It has units of newtons. And the force that it applies, if I have that's not what last time the pin failed, I took out the battery and put it back in, and it started working again. So if that doesn't work, I have another battery. By the way, you can all give Eddie Murphy credit for me saying battery all the time. It was his Delirious album, memorized it in high school. He said, "Say, man, someone stole your battery." And so I said that too. Okay. I guess I can't recommend the album because his language is really off color. It is funny, but I memorize the album, except for I don't say the words even in my head. So it's like, "Hey, man, someone stole your battery. I say we go get the," and it ends there. So if I have something like this, here's a pulley. So I'm going to write pulley so you know what I'm trying to draw here. The pulley, if it's an ideal pulley, it has no mass and no friction. Yeah, we don't make ideal pulleys, but that would be ideal. And for physics problems, a lot of the time we just say, well, let's take the ideal behavior. We can worry about reality if we have a real problem, but when we're trying to learn how things work, let's take the simple form. And so that ideal pulley has no mass, it has no friction, so all it does is change the direction of the cable. So it's not pulling or pushing on the cable in any way, it's just changing the direction. Now I have this cable, and this cable has a tension T in it. Is that cable going to put a force on the pulley? Yes. You could take practical experience. If I have a rope and I'm holding it out here and it's going horizontal and then down and it's got a backpack hanging from it, what direction is my arm's force going to have to be on that cable? Pushing out. And by Newton's third law, if my arm is pushing out on it, what direction is it pushing? It's pushing in. So we know it has to be pushing in. Well, based on the rule that we had there, answer D, which was a true statement. Remember, we're looking for the entry, so it's what's circled. What direction should the force of this vertical wire be on the pulley? I see people with their hands pointing down, but not hearing the word, but finally somebody, yes. So there should be a force of tension on the pulley that's pulling straight down there. What about the horizontal rope? And of course, I'm looking at this the opposite direction, so you're pointing the wrong way, Gabriel. No, we're just looking at opposite pictures. So yes, if you use to the left, then we can both agree. So we have these two forces of tension applied by the rope. Because the rope is leaving the pulley in two different places, and it applies a force every place it leaves an object in the direction that it leaves. So now if I add those two together, like the first problem on the test where you just had to add vectors, just had to, how do you add a vector graphically?
Tip to tail.
Yeah, tip to tail. So I could go like this or like this. And so my resultant force on there, that color was so different. It's purple versus blue. But that's the resultant force. That's the net force that the rope is putting on the pulley, just like you predicted when I used the example of if I was holding the rope. Right? Because if you have the practical experience, well, it's doing what you have the practical experience with it doing. That's why we have labs, so you see it. Now, tension is something that we have every day in life, but we don't think about that much. I especially like that our book has this top picture because 21 years ago, back when I was a monster of the gridiron, flag football gridiron that is, playing flag football at PUC, and I got my finger caught in a guy's flag belt. And this little thing here went pop. And you rely on tension. You have muscles down here in your forearm that then pull a tendon, and that tendon pulls so your finger moves. And the student whose flag I was trying to pull got in my face, thought I was trying to tackle him. I said, hey, I didn't mean to. My finger got caught. Finger all swelled up. 3 days later, the swelling went down, and I couldn't move that thing. So I had to have surgery. That's why I had the Marcazoro. Last year, my son had the same thing happen. His finger got caught in the guy's pocket playing flag football. That's why you're supposed to tape your pockets. It actually has a name. It's called jersey finger because it typically happens when people get a finger caught in somebody's jersey. Okay, so we use tension in things like controlling our muscles. We have the muscles which contract, and then we have tendons that attach the muscle to a bone so that you have a tension there that will pull the bone. Or the example here of the bicycle, you pull on the brake lever, and that pulls a cable going through all of this stuff to pull the calipers closed on the tire and make it brake. Okay, that's everyday life. A quick, how do we solve force problems, and then we'll do two problems. So steps to do, pretty much the same as what we've done in our previous problems. First, sketch your picture. So this problem was Tarzan has a mass of 84 kilograms. Find the tension in the vine if he hangs stationary. We've already actually done that problem. Was it last class period? Yeah, last period. But you first sketch, we didn't have Tarzan. We had an actual thing on the board. You sketch the picture, use arrows to represent your forces, make sure you have a free body diagram. Now remember, I am happy for your free body diagram to look like this green diagram. Why does the one in the middle, the Tarzan in the middle, why does that not work for my free body diagram?
It doesn't have all the forces.
Well, when you say it doesn't have all the forces, you're saying kind of right, but it has 3 forces instead of 2. It has an extra force. Now, is that force of Tarzan pulling down on the rope, is that a real force?
But it's an internal force.
it's a real force, but it's a force that the object is applying to something else rather than a force on the object. Our object is Tarzan, and that's not acting on Tarzan. It's acting on the rope. So that's why the green one is the correct one to use for a free body diagram. So if you draw something like this middle one that identified all the forces, that's fine. But then you need to make sure you have something that only shows the forces on the object you're interested in. So actually, previous to this step, you need to identify the object you're interested in. So I'm going to put up here 0 because that's a perfectly alphabetical. Step 0 is identify the object you're interested in. Because if you don't identify the object of interest, you don't know what to find the forces on, you don't know what mass to use. Right? You have to identify that first. So then you draw your diagram, draw the forces that are acting on the object you're interested in. Then if it's one-dimensional, you go straight to Newton's second law. If it's two-dimensional, you have another step, and that is to break into components. So I'm going to put break into components here. Yeah, that's perfect. And then apply Newton's second law. And remember, in my opinion, the biggest reason we draw this free body diagram is so we can use Newton's second law, so we can apply it. Colton has a question.
This is kind of related to what we were talking about with the rock climbing thing before, but the rope itself has weight.
Yes.
So is there a point at which you apply the rope's own weight into the tension equation?
Okay, so Colton asked a good question. The rope actually has weight. Surprise, 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 a physics rope doesn't have weight. We call it an ideal cable, and an ideal cable or ideal rope can't stretch, and it has no mass.
Cheating.
Yeah, so in our physics problems, that's just not going to occur. In real life, of course, it does. And so those are problems. If you're going to treat the mass of the rope, you have a continuous distribution of mass, and you start using calculus ideas. And so that's a good reason not to do it in a non-calculus-based class. Right, at any time you can know what the mass is, but as it's falling, how much mass is remaining, so how much is pulling down, becomes a calculus problem. Okay, so let's look at first a non-homework problem. At least I don't think it's a homework problem. We have a dude on a tightrope, and this tightrope, he's at the center, makes 5-degree angles on both sides, and our gentleman weighs 840 newtons. Now I said he weighs 840 newtons. I didn't say he has a mass of, because it has units of weight, right? Forces a weight. And then it asks us, what's the tension in the rope? And it specifies for us, the system of interest here is the point in the wire at which the tightrope walker is standing. That was given to us because you often would have said something like, well, I think my point of interest is the guy standing on the rope. Yeah, that's my object I want to look at. But in this case, I actually want to look at this little tiny piece of rope because it makes my problem simplest. So if I look at that little piece of rope, you can see the forces are already defined for me. I have the weight. Is it really the weight acting on the rope? Nope. What's acting on the rope there in a downward direction? Not gravity. Gravity is acting on the man on the rope. Right? If you're going to be technically correct, which this picture came from my textbook and they didn't worry about it, this would be, force of the man, because the force of the man is putting on the rope. Now, it turns out that if you apply Newton's second law to the man, you'd have the force of the rope on the man and the force of gravity down. Newton's second law would say some of the forces is mass times acceleration. If he's stationary, his acceleration is 0. And so you'd have those two add up to 0, and you'd immediately say the force of the rope on the man is equal to the weight of the man. And then you say Newton's third law says that the force of the man on the rope is the same as the force of the rope on the man, and that's how you get this number. I didn't write this down because I think we can all follow the logic steps in our head without doing that. But it is important to know that there is a formalism to know that while we know it's going to be the weight of the man, it comes from a more complicated set of steps. So I have the force of the man is mg, and we were given that's 840 newtons. And then I have the two tensions coming off. So at this point, we have a free body diagram. Free body diagram is rewritten down here. What do we do after we have that free body diagram? Okay, one way of doing it would be tip to tail addition. And we can solve this graphically. We can solve this graphically by doing the tip to tail addition. Sum of the force vectors is equal to mass times the acceleration vector. What is the acceleration of that little piece of rope going to be? He's just standing still. Acceleration is 0. And so the sum of the forces, using their terminology, tension left vector plus tension right vector plus the weight vector equals 0. So there I just substituted from the picture. I used just the vectors with all plus signs because they have the direction specified. And then pictorially, I can draw that as tension left. Tension right is going that way. And the weight is going like that. And we know some angles. Looking, now my angles are a little more exaggerated because I didn't want to make something super flat. But looking at this picture, we know that the angle between horizontal and the two tensions is 5 degrees. So this is 5 degrees. So if that's 5 degrees and I have vertical, which is 90 degrees from horizontal, that tells me this angle here is 85 degrees. And likewise, this angle here is 85 degrees, which makes that angle 10 degrees. Now, by the time you've gotten this far, you may be starting to feel like this was not the best approach, but it's a perfectly fine approach because I can use the law of sines. The law of sines says that opposite side divided by sine of the angle, so like W divided by sine of the angle opposite of W. Which angle is opposite of W? 10 degrees. Equals, just choose one side randomly. And that's going to allow me to, right off the bat, calculate what that tension is. Yes, ma'am.
For the mass times acceleration, is the reason that you didn't use gravity because it wasn't affecting the rope directly?
Okay, it's a good question. The question is, here I had mass times acceleration. Why did I use acceleration vector is equal to 0 and not equal to g? G is the acceleration of gravity. That's the acceleration that it would have in free fall if there were no other forces acting on it. But in this case, we look at the rope, and we have to assume that the rope's not breaking and the man's just standing there. It doesn't specifically say that he's just standing there. I mean, if he's jumping up and down, of course, that makes a difference. We have dynamically changing values. But if he's just standing there, then his velocity is 0 and it's constant. And so constant velocity means that acceleration, change in velocity or change in time is 0. So the acceleration of the man is 0 because he's stationary and not changing that stationary state. Okay, did you get a question for me or answer for me, Jonathan?
I got 4818.95. 4818.95.
Okay, and we only have 3 significant digits. So putting that to the proper significant digits, 4,820 newtons. That's a much, much higher tension than the weight of the man. That's one way of solving the problem. And if you only have 3 forces, that may very well be the best way to solve it. If you have more than 3 forces, you're going to have to go to a more systematic method because your geometry generally gets untenable. And so what's the more systematic method? That is to break things up into components. Now notice X and Y are already defined for me. So using that, I'm going to have my horizontal or X direction and my vertical or Y direction. And I'm going to break each vector into its components. So I will have the tension right vector is equal to, and so the tension right vector, if I'm going to break it into components, here's the tension right in the X, the tension right in the Y. This angle here is given as 5 degrees, 5.0 actually. And so I simply say, aha, use my trigonometric functions that relate the hypotenuse, which I'm looking for tension right, with the adjacent and opposite sides. So, well, sticking with the picture here, the adjacent side is tension right in the X direction. So I'm going to have tension right times cosine of 5.0 degrees in the X direction. Remember, there's a redundancy because the X with a hat over it, the X, we say X hat in math, X carré if you're not doing math, that means in the X direction. So there's a redundancy in the way I do this, but it separates things out. So there's my, oh shoot, I ran out of space. There's my first force, my second force, tension left. It's in the negative X direction, so I put that out in front. How do I get the negative X direction? Because X is to the right and tension left is coming out here to the left direction. So that's where I got negative. It's the opposite of this. And then continuing on, plus tension left, sine 5.0 degrees, y hat. That's 2 forces. I have 1 more force remaining, which I can fit in here. That weight force in the X direction, there was nothing in the X direction, right? This force right here was all vertical, so all in the minus Y direction. And we actually had a number, minus 840 newtons in the Y direction. So there I've broken things down. I'm going to have to add another page here. Bear with me just for a second. Insert one page. Oh, that scared me. So there I've broken down my components in the X and Y direction. I did this so I could use Newton's second law. So I'm going to first do Newton's second law. Actually, I think that this will work for me. Wrong button. That is not what I intended. Where do I hit? There's undo. This button. Duplicate. That's not going to work. Forget it. Delete. I'm just going to come over here and continue on the next page using that information. So I'm going to take sum of the forces in the y direction, that's special, for people over there at Southwest, my pen stopped working again. You heard people laughing. That must be my sign to change the battery. No, it's still not working. Yeah, that's not good. Good times, they're here to stay. My goodness. Well, that is another difficulty that I did not expect to happen. Blame it on the technology. I'm going to have to just raise the screen and do the rest of the problem on the board, which has the drawback of there's writing on the screen or on the board. So change the camera over. Yep. So sum of the forces in the y direction equals from the table, which obviously you cannot see now. Yes, sir.
Is there a way to turn on the projector? It makes it hard to see it.
Yes, I can. Okay. Sum of the forces in the y direction. Notice I put in my table tension left and tension right. But the tension in the cable should be continuous throughout. And so I really didn't need to do tension left and tension right. I could have just put tension because it's the same for both. So now I'm going to just write tension sine 5.0 degrees. That's what I had from tension right. From tension left, I had tension sine of 5 degrees again. And then finally, from the weight of the man, I had minus, because it was down, 840 newtons. So that's the sum of the forces in the y direction on the tightrope walker. That should equal the mass of that little piece of rope. How much is that little segment of rope's mass? I don't know. It better not matter or else this is going to fail. What's the acceleration of that little piece of rope? 0. Hooray. That means it doesn't matter what the mass was. So now I can take this and I can immediately solve for the tension. That is, actually, yeah. Stupid thing. Bring it back here so they at least have down the corner of the table with the variables. You guys can't see it, but they can see the corner of their screen with the variables are. Solve this for tension. 2 tension times sine of 5.0 degrees equals 840 newtons. That better give us the same answer. You notice that's a distinctly different way of solving the problem. This is the way I usually solve them, so I have more confidence in this.
Same answer. 4820.
So there's 2 different ways of solving the problem. One was using a graphical method, which I think we would probably all agree, in the end was the simpler method. This method here, though, is the one that you're going to have to use in a bigger problem. Now, I'm going to turn this back on just for a moment and go to the next slide. It's another problem, and then we will work on solving that problem. So in the Southwest, you can change back to the other video feed to see the problem. This is one of your homework problems. As you can see, it's problem number 3 that is due tonight at 7:35 p.m., which Actually, I think that's right at sundown. I think I screwed up on the time, but what are you going to do? So we have two masses. Mass 1 is 13 kilograms. Mass 2 is 7.5 kilograms, attached by an ideal rope, a rope that has no mass and does not stretch, going over an ideal pulley, a pulley that has no mass, no friction. And then we're asked to find acceleration 1, acceleration 2, and then put those two equations together to find acceleration and finally the tension. So I'm going to go ahead and work this problem. I'm going to just redraw the picture on the board and do it on the board because I've lost my ability to write. Just double check in case it came back for some reason. Okay, my best version of the drawing. The numbers that we had were mass 1 is 13 kilograms. And mass 2, 7.5 kilograms. And then we have the four parts of the problem. A, what is acceleration 1? B, what is acceleration 2? C, what is acceleration? D, what is tension? Actually, it says acceleration 1, but it's a number. And tension is going to be a number. Now, there are a few more parameters I didn't mention on the answers, or the questions. For part A, it says, assuming friction is negligible. Okay, we're assuming that. We're assuming no friction. We're going to write an expression for the acceleration the block mass 1 has in the x direction. And it specifies for us x and y. So what is acceleration 1 in x direction? It's important to define the direction because if it was in the minus x direction, you'd have the opposite sign. Part B says to find the acceleration in the y direction. So that means we're going to find the acceleration in the upward direction for mass 2 for part B. So I've got the problem laid out. I'm ready to start. I did not do that. This is probably super dried out because that was from yesterday. How do I start this?
Which one do you want?
I'm going to do part A first.
Well, just make the equation.
Okay, I need to find the equation for acceleration, but before I do that, I need to make a free body diagram for mass 1 because that's the object of interest for part A. So for part A, I'm going to try this pen that's been sitting open for the last day. Yeah. So for part A, here's mass 1. What forces are acting on mass 1? Name every force you can come up with.
Tension.
Okay, I had tension, I had gravity,
Normal force.
normal. Okay, those are all three of the forces. Because it said no friction, that's the end. So now we have to always define directions. What direction will tension be? To the right. So there's my force of tension. What about the force of gravity?
Down.
Okay, and what about the force normal?
Up.
Now, two of those were reasonably obvious. How did you get up for force normal? Just to make sure we're on the same page.
Sitting on the
Okay, it's coming out of the surface. It's a horizontal surface, so it's coming up out of it. Now, the problem asked me to find the acceleration in the x direction. So when I do my work, I'm just going to do sum of the forces in the x direction. I skipped the step on break the forces into components for a very simple reason. They're already broken up into the components. So sum of the forces in the x. Look in this picture. What forces do I have in the x direction? Just the tension. So, what is acceleration 1 equal to?
Tension over mass.
Now, in this problem, T is the symbol used for the magnitude of the tension. So the force of tension has a magnitude of T. And so in terms of putting my answer, T divided by M1. I don't know the tension yet. It says to put your answer in terms of the tension. And actually, if I recall right from when I did this, I just put T over M1 for my answer. You click T, click M1. That's the easiest way to make sure it's entered right. So there's my answer for part A. Was that a difficult job? No. But you have to know the steps. As long as you know the steps, it comes real quick and easy. So let's go to part B. Part B is looking at mass 2. So I draw a different free body diagram for mass 2. So for mass 2, what forces are acting on mass 2?
Tension, gravity.
Tension and gravity. That's it. No force normal. Why no force normal?
This is not
Not sitting on a surface. Excellent. It's always distressing when, like on a test, somebody tries to put a force normal where there is none. So that's why I keep asking questions like that. It asks us to find the acceleration in the y direction. Convenient enough because it's the direction of the forces. Newton's second law. Sum of the forces in the y direction is m2a2. What should I substitute for sum of the forces in the y direction?
Ft minus Fg.
Okay, I had Ft minus Fg, or mg, whichever one you said. That's correct. Now, I'm going to specifically ask this to the people of Southwestern because they have to turn on the mic and it's hard for them to answer when I ask questions to everybody. So how is it that he was able to choose those two and decide which one was positive and which one was negative? So Southwestern students, got to turn on the mic first. You guys do hear me, right?
Yes, we hear you.
Okay. So can one of you tell us how he knew that force tension would be positive and force gravity 2 would be negative?
Is the direction?
Okay, because of their direction.
Specifically, chose y to be upward positive.
Excellent. We chose y to be upward, and since force tension was upward, it was the same direction, it was positive. Force gravity 2 was the opposite direction of y, so that's why it's negative. So now we want to find the equation for acceleration 2 from this. So just divide both sides by m2. I'm going to substitute now force gravity 2 as m2g. You see that the m2 is canceled in that second term. And making the substitution again that force of tension has a magnitude of tension. That gives me tension over m2 minus g. So there's our answer for part B. Now I know for everybody so far, this is exactly what you're putting in for your answers. But I'm hoping that you're learning about the process by seeing this problem done. It will save you some time doing homework tonight, sure. But it's the learning that's the important thing. That's why we assign homework. So I have A and B done. Now we get to C. We want to get a number for A1. We couldn't put a number in here because we did not know the tension. we couldn't put a number in here because we did not know the tension. It gives us a hint. It says, looking carefully at the relationship between acceleration 1 and acceleration 2. So I will lead you through this rather than, I could ask, I'm sure somebody would know the answer. Let's say that M1 moves forward 1 centimeter. How does M2 move? Downward by how much? 1 centimeter. So right away we can see motion in the positive x direction for M1 translates into motion in the negative y direction for M2. And so if we take the change in motion, we're going to have the same relationship. The change in velocity will have the same relationship. So we're going to have, because they're tied together and by the definition of our directions, that A1 is equal to minus A2. That's because of the way the problem is set up. And so now I have two equations with acceleration and tension, two unknowns in each one. I want to find the acceleration, so I'm going to first just replace, well actually, acceleration 1 is minus A2, or acceleration 2 is equal to minus A1. Those are equivalents. Because I'm asked to find acceleration 1, I'm going to substitute in this relationship so that it's in terms of acceleration 1. But I want to get rid of tension. So I eliminate tension, just solve this for tension. So if I solve this first equation for tension, it's very simple. You multiply both sides by M1, you have tension is equal to A1 M1, or what we have right there. So tension is A1 M1. Substitute that into this equation, and I will have A2 is equal to minus A1 equals A1 M1. There's my substitution for tension, divided by M2 minus G. So at this point, I can erase the A2 now because I have acceleration 1 is my only unknown. And so to solve for acceleration 1, clearly I have to get the accelerations on the same side. I'm going to do that by adding A1 to both sides and adding G to both sides. So I'll have an equation that says G equals A1 times M1 over M2 plus A1. Factor the A1 out, so the right side has A1 multiplied by M1 over M2 plus 1. And now I'm ready for my last step. Divide both sides by the term in parentheses so I get acceleration by itself. I am guessing, I actually discovered that you can remove the little thing there that shows the pictures, but I'm guessing the people of Southwestern, can you see what I just wrote? Yes? Okay, good. I'm guessing you can't see much further down though, right? So I'm gonna move over here to finish off so you can see it. I gotta check this
I can
one more
always
time.
adjust the camera to make it look down more.
So there's my equation. Now everybody has a different set of mass 1 and mass 2, so the answer that people get is going to be different for every person. But here's our equation to find the acceleration. So given my numbers, I would have that 9.80 meters per second squared divided by 13 over 7.5 plus 1. And it's a little different than dividing by 2, but somewhere in the ballpark of, let's say, 5. Yeah, go ahead and get. It feels so unfulfilling to get here and then not get a number. I actually did this last night, but I'm going to remember a number.
3.585.
Very close to not 5. 3 point what?
3.585. So 3.59.
Was it 5850 or 58?
Oh, 5853.
Okay, just making sure it rounds up. I see people grabbing their bags. Am I out of time?
Yeah.
Ah, crud.
Yeah, we can do the next one. That's okay.
Well, all you have to do for the last part is put it back into this equation, solve for tension. You already have the equation. Okay, wow. A nice use. If you ever get your car stuck, you can use physics. Tie a rope to a tree and pull the rope sideways. Because as you saw, the tension that we calculated here with the tightrope walker, far, far greater than the force of the tightrope walker. So you apply a force of, let's say, 100 newtons to that rope, you can have it, 1,000 newtons that it's pulling on the car. Smart, right? Using physics. All right, have a great weekend. Enjoy the lunar penumbral eclipse that's occurring right now that we can't see because it's not nighttime.